Hello and welcome to my talk about what the Z-transform is and how it can be used to implement real-time data analysis. So to maybe warn you in advance, especially the first part of the talk will be quite mathsy because it contains some derivations and so on, so you understand where the Z-transform comes from. But then if you stay with me, you'll be rewarded in the second half because there will be hopefully many helpful examples that are there to illustrate how to use the Z-transform in practice and what it really can do. But let's maybe start with some basics and then by some basic maths. So what is the motivation? Why do we need something which is called the Z-transform? So the ultimate goal is to, for example, implement something like a high-pass filter or some kind of frequency filter to some discrete stream of data. And there are now basically two options we could think about. The first option is the conventional one, maybe. So if that's stream of data, I could just take maybe the last chunk of data from the last 1 second, for example, do a Fourier transform, then filter this Fourier transform, and then do an inverse transform to get the filtered signal. The problem with this is that this is not real time, so you always have to wait for 1 whole second, for example, then do a Fourier transform of this 1 second to get the filtered data. So this totally works, but it's not real time. The other alternative contains so-called input-output algorithms, which might look like this. So imagine, for example, you've got a discrete stream of data, xn. So for example, x1 is the data point after 1 second, x2 the data point after 2 seconds, x3 after 3 seconds, and so on and so forth. And then you use an algorithm to calculate the outputs yn. So y1 is the output after 1 second, y2 is the output after 2 seconds, and so on and so forth. And the goal is now to, in the end, create algorithms that treat different frequencies in the way we want them to treat them, right? So this example here, for example, would suppress DC, so would suppress DC signals, so signals with frequency 0, because in this example we are basically subtracting two consecutive inputs to get the output. So if the inputs are always the same numbers, then the output will always be 0. So this algorithm specifically will block DC signals. Right, and the question now, generally speaking, is how do I get from my specific algorithm to my transfer function, so the function which tells me which frequency is amplified by which factor. So in this example, the frequency 0 would be completely suppressed, and the frequency pi, for example, would be strongly amplified. So how do I get from algorithm to my transfer function, and also vice versa? So how would I get from my maybe given transfer function to an algorithm that does that transfer function? And the advantage of that is, of course, that this is real time. So I can get my output after n seconds, yn, by directly plugging in my input after n seconds without having to wait for 1 second as I would have to do in the Fourier approach. So this is what the Z-transform will in the end do. And so transform between the algorithm and the transfer function and vice versa. And we now want to find out how that works. One thing we need to know about is the Nyquist theorem and how to represent frequencies on the complex unit circle. So you might know that sampling too slowly can lead to wrong conclusions. So for example, if my real signal is the blue one, so the real signal is oscillating quite fast, and my sample rate is too slow, I might come to the wrong conclusion that this orange curve is the real signal, even though actually the blue curve is the real signal. And that is the Nyquist theorem. So if my sampling rate, so the rate at which I take my data points, is fs, then I can only make statements about the frequency range between minus sampling rate over 2 and plus sampling rate over 2. That is the Nyquist theorem. So for example, if my sampling rate is 1 Hz, then I can only talk about the frequency range between minus 1/2 and plus 1/2, or about the angular frequency range minus pi to pi. Of course, if my sampling frequency is not 1, then that will just work the same, but it requires some scaling then. So let's just assume, for the sake of simplicity, that my sampling rate is 1 for this presentation. So in that case, my angular frequencies will be in the range from minus pi to pi, so it totally makes sense to represent them on the complex unit circle. Right, so this point, so the 1 on the complex unit circle represents the frequency 0. This point, so I, stands for pi over 2, because e to the I times pi over 2 is I, and so on. So every point on this upper half stands for frequencies between 0 and pi, and every point on this lower half stands for frequencies between 0 and minus pi. So we can easily represent frequencies on the complex unit circle because we're bounded by the Nyquist theorem, so we can't talk about frequencies outside of the range from -pi to pi in this case, so it totally makes sense. And that also means that I'd like my transfer function, which tells me how a specific algorithm behaves concerning different frequencies. I would like this function to live on the complex plane. And I would also like the function to fulfill the property that if I plug in a value on the complex unit circle, that this function will then give me the output to input ratio of the algorithm if I plug in a signal of that frequency. So for example, if I plug in e to the I times pi over 2, so I, in the transfer function, I would like the output to be the output to input ratio of the algorithm if I send in an input signal with a pure frequency of pi over 2. So my goal in the end is to find this transfer function that lives on the complex plane, and the important part will happen on the complex unit circle. Okay, and one more thing I would like my transfer function to do is to tell me something about the stability of the algorithm. So if you maybe look at these two algorithms, you might quite fast see that they're almost the same apart from the coefficients I marked red, right? So this algorithm on the left, for example, computes the output after n seconds by using the output from 1 second before and doubling it. So I think it intuitively makes sense that this algorithm will not be stable but will blow up as time proceeds. Whereas this algorithm is taking the output from 1 second before and halves it. So it makes sense that this algorithm probably will behave stably. So some algorithms are stable, some are unstable, and the ultimate goal would be that our h function somehow also tells us something about if the whole thing is stable or not. And we'll find out in a few slides how that works. But let's first find a term for the Z transform. So the Z transform is basically the thing that will take us from the algorithm to the transfer function in the end, and you'll see in a few slides how that works. So if you maybe recall how the discrete Fourier transform looks like, this is looking for frequencies in discrete signals. So the discrete Fourier transform is asking which frequencies are contained in this discrete signal yn in that case, right? And to find that out, it multiplies the discrete signal with e to the minus I omega n, so with a pure oscillation, and sums up all these parts to find out which frequencies are contained in the signal. Now the Z transform, which is meant to give us the transfer function in the end, is not only supposed to find out which frequencies are contained, but also how fast a given process is decaying or blowing up, because we'd like the transfer function to tell us something about frequency as well as stability, so decay or blowing up. So to find out something about stability and decay, I'll just do the same thing as the discrete Fourier transform does, but I'll also multiply by r to the minus n to find out first what the frequency components are of the signal yn, and second what the decay components are of yn. So the Z transform is basically a more general version of the discrete Fourier transform. I can then rearrange these terms and simplify it a bit, and I will then get a complex number z equals r to the I omega t to the minus n, and this is the general form of the Z transform. So the Z transform of a sequence yn is defined to be the sum over yn times z to the minus n. And you'll see in a few minutes how this will actually lead us to the transfer function we would like to have. Okay, but now let's spend a few minutes on trying to mathematically understand what this Z transform does. So the following slides do not have any physical context. They're just meant to show you what the maths of the Z transform is, and that it's nothing magical, but that it's quite easy to use it, and maybe to get you feeling what the Z transform does to certain basic sequences. So maybe don't try to find the physical meaning in the following slides. I'll come back to the physical meaning and how to get to the transfer function after this short chapter on maths. So just again the definition, the Z transform of a sequence is defined as this sum over yn times z to the minus n, and the Z transform of the sequence yn is sometimes also called just capital Y of z. Okay, if you look up the definition on Wikipedia, for example, you will sometimes find that the sum starts at negative infinity, which is also correct, but in our physical context, we assume that the measurement starts at t equals 0, so I don't have any outputs for negative times, so I assume all these y's to be 0, which is why I can just start my sum at 0. Okay, so let's now find out, just to understand the Z-transform mathematically without physical context, what the Z-transform of a few basic sequences is. So for example, the single pulse sequence, so the sequence delta n in that case, which is 1 for n equals 0 and then 0 forever. If I plug this into the Z-transform definition, what I get is this. So the Z-transform of delta n is also written down as capital delta of z, so that's just notation. This is defined as this sum. I can then expand this sum to get this, and then I might see that, well, all my deltas, apart from delta 0, are 0. So all these terms which contain a z disappear, and I'm left with delta 0, but delta 0, according to the definition, is 1. So the Z-transform of this single pulse sequence is 1. And if you want to have a physical interpretation of that, maybe think of it as the Fourier transform of a delta function, which is also 1, because delta of x contains basically all frequencies, so the frequency spectrum is flat. But seriously, you don't have to interpret that now, so this is just to show you the basic maths and that the whole thing is nothing but calculating infinite series. So nothing special about the Z-transform so far. Second example, the all ones sequence, so un equals 1 for all n, works just the same. So the Z-transform of un is also written down as capital U of z, is defined as this series. All un's are 1, so we're left with 1 plus 1 over z plus 1 over z squared, and so on and so forth. And you might recall the geometric series, so a series like this always equals 1 over 1 minus x, and I can use that to calculate what the term from above is, and by doing some quite easy simplifications, we'll get that the Z-transform of this all one sequence is z divided by z minus 1. And again, there's not necessarily physical context, this is just to show you that the Z-transform is nothing magical, and for the basic sequences it's not too hard to calculate what it is. Last example, the exponential sequence. So what happens to something like 2 to the n, or 3 to the n, or e to the n? Or, well, I can also use that then to calculate the Z-transform of the sine of n, for example, because the sine or the cosine function can be described as the sum of exponentials of e to the I omega n's and so on. So this is a quite useful thing to know. Well, same thing. So the Z-transform of fn is also written as capital F of z, is defined as this infinite series. If I expand that, I get this term, and by using the geometric series once again, I get that the Z-transform is z divided by z minus a. Right, so that's, again, nothing magical happening. I can just use the definition of the Z-transform to calculate the Z-transform of any arbitrary sequence I like. Okay, so far so good. Let's talk about one more quite useful property of the Z-transform, namely linearity. So you might see that the Z-transform only consists of summing things up, so it makes sense that the whole process behaves linearly. So if I take the Z-transform of the sum of two sequences, I could as well just take the Z-transform of the single sequences and then add them up. Also, if I multiply my sequence by a constant complex number a or b, I am allowed to factor this number out and just take the Z-transform of the sequence. So this is what linear means, and this will make a lot of our derivations easier, because we can just, instead of taking the Z-transform of a whole infinite series, look at the single Z-transforms of the components of the infinite series. Okay, and one more, even more important property is the so-called shifting property. So the shifting property is trying to make a statement about what happens if you take the Z-transform of a shifted sequence. So we already know what the Z-transform of something like yn is, but what happens if I look at the shifted sequence yn minus 1? And that's also quite easy to see. So the z transform of yn minus 1 will then contain a y minus 1 term, so that one, but we agreed on these terms being 0, so I can forget about this term, and then factor out the z to the minus 1. That will give me this, and I'll then quite easily see that the things in the brackets are just the normal z transform of yn, which can also be written as capital Y of z. Right? So the z transform of a shifted sequence shifted by 1 is z to the minus 1 times the normal z transform. And this can quite easily be generalized, so the general rule we'll need later quite many times is this. So the z transform of the sequence yn but shifted by k is z to the minus k times the z transform of the non-shifted sequence. And this is something you might have to recall for the derivations to come. Okay, so far so good. So that's all I wanted to say on the basic maths of the Z transform. Now let's go back to some applications and maybe also intuition. So the goal in the end is to first learn how to use the Z transform to get the transfer function of a given algorithm, and then also to get an algorithm from a given transfer function. Okay, so let's start by a quick comparison before we do that to a more specific example. I'd like to compare the Z transform to the Fourier transform in the light of continuous convolutions. So if you recall these algorithms I showed you at the start, they look something like this. So yn is equal to some combination of previous inputs and previous outputs. So the most general version of writing down such an algorithm would be this, right? So yn is some combination of previous inputs, so xn's, and previous outputs, soyn's. And if you have seen continuous convolutions before, you might realize that this looks quite similar. So this is the definition of a continuous convolution, and you might notice the similarities, right? So in the convolutions, there are these t and x minus t parts. Over there are these k and n minus k parts. So what's effectively happening in these algorithms is we're convoluting these coefficients, so the impulse responses they're called, with the input and output sequences. So there is some formal similarity, and actually, well, the right thing is called a continuous convolution, and these left sums are actually called discrete convolutions. So actually both these terms are convolutions. And as you might know, what a Fourier transform does to a convolution is it turns the convolution to a multiplication. So we often use Fourier transforms when we have continuous convolutions because that makes the whole calculations more easy. And this is actually what the Z transform does to discrete convolutions. So as we'll see in one slide, the Z transform also turns the discrete convolution into some kind of multiplication, just like the Fourier transform turns the continuous convolution in some kind of multiplication, which well, makes handling these algorithms a lot easier, because by using a Z transform we can forget about these like complicated sums and use simple multiplications. Okay, so let's try to do that. So let's start with the most general algorithm we can think of, and let's try using the Z transform to, in the end, derive an equation for the transfer function h. Okay, so applying the Z transform on both sides, we need this shifting property again we talked about a few minutes ago, and this yields this, right? So applying the Z transform on the left just gives capital Y of Z as defined. Then the Z transform of this whole sum is, due to linearity, just the Z transform of the single x and minus k's. But the Z transform of x and minus k, according to the shifting property, is just set to the minus k times x of z, and the same thing over here. So we've used linearity as well as shifting property now. Going on, I can now rearrange it a bit, so I can pull this sum to the left, I can factor y out, I can then find the output to input ratio, which is my transfer function. So y was the output, x was the input, so my transfer function is y divided by x, which is the fraction shown here, so the one sum divided by 1 minus the other sum. And this is the most general result you can get for the most general transfer function. Okay, so this is now supposed to tell us something about how this algorithm, which we started with in the first line, behaves by looking at the values of this function on the complex unit circle, as we said before. Okay, so let's now, so that was the end of the mathsy part, or of the very mathsy part. Let's now look at some very basic examples to maybe understand that in a maybe more specific way. So let's look at the algorithm we started with at the beginning, so this DC blocking algorithm. So again, this algorithm is receiving its output by subtracting the last two consecutive inputs. So if the signal is a DC signal with frequency 0, so static, then the output will always be 0, obviously. So hopefully this H function, this transfer function, will in the end tell me that frequencies 0 will be completely suppressed, whilst other frequencies might be even amplified. So this algorithm should serve as a high-pass filter. So to get the transfer function, let's apply the Z transform on both sides. So the Z transform of yn is, as always, y of z. Z transform of xn is x of z, and of xn minus 1 is, using the shifting property, z to the minus 1 times x of z. Factoring x out and then rearranging yields the transfer function 1 minus z to the minus 1. So now looking at the values of the magnitude of this transfer function on the complex unit circle should tell us something about what the output to input ratio at these different frequencies is. And we're expecting the transfer function to be 0 at 1, because 1 corresponds to e to the I times 0, so to frequency 0, and that is actually what happens. So this is a 3D plot of the absolute value of the transfer function on the complex unit circle, and you might see that there is a root, and this is where the number 1, so e to the I times 0 is. So actually we've now proven that this algorithm serves as a complete DC suppressor. So DC signals will be completely suppressed, whereas signals of higher frequency will be increasingly amplified, and then there's a maximum at pi or minus pi. It's obviously symmetric. So you'll get the transfer function in the 2D version by just like copying the red line into a 2D coordinate system. So this root belongs to this, and so on, right? So you can always get from these 3D plots to the 2D plots by just looking at the red line, so at functional values above the unit circle, basically. And as I already told you, this thing does what it's supposed to do. So the value at 1 is 0, which means that DC is blocked, and the value at pi, at e to the I times pi, so at minus 1 is maximal. So frequencies pi or minus pi, as you wish, are maximally amplified by this algorithm. Okay. So this is how you derive transfer functions in a very general way. Always start with the algorithm, then apply the Z transform, then rearrange the terms to get y over x, which is a transfer function, then plot that over the complex unit circle, maybe do a 2D plot, and then you'll know how this algorithm behaves. In this case, indeed, as a high-pass filter. Okay. Now I promised that this H function also tells us something about stability. So let's again consider this algorithm, which basically gets the output after n seconds by multiplying the output from before by a coefficient a. So this is a recursion. And I think it's quite clear to see that if this a coefficient I've used there is larger than 1, then the whole thing will blow up to infinity. So will be unstable. If it's less than 1, the whole thing will be stable. So I guess this is intuitively clear, and let's now try to get the same result by using the transfer function. So therefore, again, let's apply the Z transform on both sides. So yn becomes y of z, xn becomes x of z, yn minus 1 is z to the minus 1, y of z, and so on and so forth. So rearranging, again, gives us a transfer function, which in this case is 1 over 1 minus a times z to the minus 1. So to find out if the algorithm is stable, I would like now to look for where the poles are of this transfer function. So where this transfer function is infinity, if you want, or in other words, where the denominator of this fraction is 0, because that's where the poles are. And you can easily check that this is the case at z equals a. So if you plug in z equals a into this fraction, you'll get 1 over 0, which is a pole. And now that tells us something about the stability. So if this pole is located within the complex unit circle, that means the magnitude of a is less than 1, then the whole thing is stable. If it's outside the complex unit circle, then the whole thing is unstable, and this is when the magnitude of a is larger than 1, which is exactly what we expected from our intuition before. So as a general rule, if the poles of the transfer function are all within the complex unit circle, the whole thing, the algorithm is stable. If not, then it's unstable, or it might at least be unstable. Okay, that was a lot to swallow. To summarize this first applications chapter, so the values of the magnitude of h on the complex unit circle tell us how the algorithm treats signals of different frequencies, and the location of the poles tells us whether or not the whole thing is stable or not. One thing I've not talked about yet, which will be a part of my last chapter, is how to manipulate the transfer function to make custom designed algorithms. Right, so what we've done now is we started with a given algorithm and then computed the transfer function. I could also think of a transfer function and then basically go the path backwards to find out what the algorithm must have been, and that's how I can build custom designed filter algorithms that do exactly what I want them to do. So this will be part of chapter 4, which is my last chapter, applications of the inverse Z transform, or how to create custom designed algorithms. Okay, to do that, let's maybe start with a very easy example. Let's start with this. So what we want to find is a stable algorithm, so only poles in the complex unit circle, that amplifies signals with a frequency of pi over 2. So I want a transfer function which has large values close to e to the I times pi over 2, which is I. So I could, for example, choose a pole at I over 2. I can't choose a pole at I directly because that would make my whole thing potentially unstable, but I can choose poles arbitrarily close to I over 2, and depending on how close my pole is to I over 2, my transfer function later will be broad or narrow. So I over 2, which is one possibility. I could also use 0.999i, right? So if that's my complex unit circle, there is I, then in that case I chose my pole to be at I over 2. That is basically a random choice. So I could also go with 0.8i or something else. So I want a transfer function h with a pole at I over 2, and the most basic I could think of is this. So this definitely has a pole at I over 2 because the denominator is 0 at I over 2. The only problem is, it's not really a problem, but if I used this transfer function to get my algorithm, then my algorithm would contain complex coefficients, which might be a problem. So if I want real coefficients, then I'll also have to use real polynomials. So that means in this case I would multiply the denominator by the complex conjugate to get maybe this polynomial, and that works as well. So now I've got poles at I over 2 and minus I over 2, which is still alright, but this definitely works. So if you plug in I over 2 for z in this function, then you'll have 1 over 0, which is a pole. So let's try to now get to the algorithm starting from this transfer function. So we have to go the inverse path of the path we went before. So starting from the transfer function, which is y over x, so output over input, we can rearrange these terms to get this. So just like pulling x to the right and this denominator to the left and so on. And I can then use the inverse z transform, which is a quite easy thing. So for example, yz is yn, then z to the minus 2y of z is yn minus 2, and so on and so forth. And there we are, we're done. So even though it might seem strange at the beginning, when you've done that a few times, it's really trivial. So just think of any h function you like, then rearrange a bit and do the inverse Z transform to get your algorithm in the end. So this algorithm should amplify pi over 2 frequencies. So to prove that, let's maybe look at the magnitude of the transfer function again in a 3D plot, and this looks like this. And it does the thing we wanted it to do. So it does not really amplify frequency 0, then it goes up, it strongly amplifies frequency pi by 2, and then it again not really amplifies frequencies pi. And obviously it's symmetric because we chose the poles to be symmetric in the course of not wanting to have complex coefficients. So the 2D version of this red curve looks like this. You could also just look at the right half, because obviously it's symmetric because we're dealing with real polynomials, and as you know, if the complex number z is a real polynomial, it's a root of a real polynomial, then the complex conjugate of z also is a root, so the spectrum will be symmetric. So we can just look at the right half, and as you can see, frequency 0 will be multiplied with 0.8, so attenuated. Frequency pi by 2 will be amplified with a factor of 0.3 something, and frequency pi will be attenuated again. So it worked. One last example. I want to find maybe a bit more complex algorithm, but not too complex, so my algorithm should please completely suppress DC signals and strongly amplify signals of frequency pi. So I would want my transfer function to have large values close to -1, because that's e to the I times pi, and a root at 1. So I could, for example, choose my pole to be at -0.9, or -0.8, or -0.999, doesn't matter, and my root has to be at z equals 1. So if this is my complex unit circle, I'd like my pole and root to be there, for example. So let's find a transfer function which fulfills that property, and one example would be this. So you can check that yourself. If you plug in 1, then the numerator will be 0, so that's a root. If you plug in -0.9, then the denominator will be 0, so that's a pole. And again, going back from that, so starting at y over x equals this fraction, rearranging and using the inverse Z transform. So y of z becomes yn, z to the -1, x of z becomes xn minus 1, and so on and so forth, yields this algorithm, which should first completely suppress DC, and second strongly amplify pi frequencies. So to make that clear, let's look again at the 3D plots, which looks like this in this sense, in this case. So here is the frequency 0 at e to the I times 0, which is 1. You can see the transfer function has the value 0, so DC is indeed blocked. And there is the pole at -0.9, and then this this red line basically goes behind the pole, so I included another image which looks at this graph from behind, which looks like this. So we can see that this red line actually goes around the pole. It has a finite value at -1, so the pi frequencies are strongly amplified, but not amplified with an infinite factor, which is good, because that would make the whole thing unstable. So the 2D plot looks like this. 0 is suppressed, and pi is strongly amplified with a factor of 20 in this case. As some bonus content, what would happen if I had placed the pole at -1, not at -0.9, sorry. Well, as I said before, placing the pole on the complex unit circle will make the whole thing unstable. So in that case, my red line would not go around the pole, but would go like up with the pole to infinity and then come back down again. So the pi frequency would be infinitely amplified, and all other frequencies would be basically ignored, which would make the whole thing quite unstable. And one more bonus, so you see this actually works. So I used Python to generate 100 random numbers between -1 and 1, and I assumed a sampling frequency of 1 Hz, and I then first made a Fourier spectrum of the inputs of these random numbers, which looked quite evenly distributed. I then computed the outputs by using the algorithm we just computed. So we are expecting this algorithm to completely suppress DC signals and to strongly amplify signals of frequency, well, of high frequencies, and actually that works. So this is the spectrum of the output signal, so of Yn, and as you can see, DC is all around DC is strongly suppressed, and high signals are strongly amplified. Right, so that was it. So I hope I could help you understand the Z transform. So you can use the Z transform to first analyze given algorithms on stability and frequency response, and also vice versa. So you can use the inverse Z transform to first create a transfer function and then use the inverse Z transform to find the corresponding algorithm to implement your real-time data analysis in your data processing codes. So that was it. Thanks. These are my image sources. And if you've got any questions or recommendations, please put them in the comments. And if you have been, thanks for watching.